total internal reflection. Total internal reflection. Very important point, which proves diamond glitters more. It is because of the principle of total internal reflection. Optical fiber principle, total internal reflection. Then what is called total internal reflection, sir? You have a medium, this is normal. This is air, this is denser medium. Air medium, denser medium. Now you are allowing some light to be incident. What the law says, denser medium to rarer medium light travels means it bends away from the normal. Bends away. This is I, this is R. This already we know. Now you increase the angle of incidence. I is equal to IC. IC we call it as critical angle. When the light is incident at critical angle, the entire light, refracted light, grazes the surface. It will not go to the other medium, rarer medium. It grazes the surface. That means R is equal to 90 degree here. Suppose I am allowing the light to be incident greater than critical angle, I greater than IC. There is no question of reflection. There is no question of refraction here. The entire light is reflected back, turned back. This is called total internal reflection. The angle of incidence should be greater than critical angle. Greater than critical angle means no light will be refracted. The entire light is reflected. So only diamond glitters more. Light is not refracted. Whenever you see the diamond, at particular point is glittering. Any direction you change, it is glittering. The light which enters is not passing through, it is getting reflected back. So you are getting more glittering in the case of diamond. Refractive index is more. That's all. Sir, how to calculate the critical angle? If you know the refractive index and angle of incidence, critical angle can be calculated. You see here. Mu is equal to sin I by sin R. When I becomes IC, what happens to R? R becomes 90 degree. Angle of refraction is 90. Therefore, mu is equal to sin IC by sin 90. What is sin 90? Ma? Sin 90 is 1. So I can write mu is equal to sin IC by 1. Sin IC is equal to mu. IC is equal to sin inverse of mu. So, clear? So this is the condition for total internal reflection. Okay, next one. Sir, this mu, you can write it as second medium to first medium, mu1 by mu2. Mu1 by mu2 means mu1 is first medium, air medium. Mu2 is second medium. Refractive index is mu. So correctly speaking, we should write 2 mu1. That is mu1 by mu2. Mu1 is 1 for air. So 1 by mu is the answer. If you want to represent the formula in terms of two different refractive indices, like this you have to write. Next, refraction through a prism. The derivation is so big, we are not going to see the derivation. We are going to confine for definition only incident ray, refracted ray, emergent ray, like that, and final formula. Sir, this is a prism. ABC. This is normal. Normal. Extend the normal, extend the normal. Both the sides we have normal. Normal means perpendicular. Allow light to be incident. PQ. Incident ray. QR. Refracted ray. RS. Emergent ray. This is incident ray. This is refracted ray. This is emergent ray. Extend this. Extend this. This should be the actual incident ray direction. But light is coming here. So between these two, we call it as angle of deviation. Angle of deviation. If you say A is the angle of the prism, and there is one concept known as minimum deviation. Generally, D is called, small d is called deviation. What is the lowest value of the deviation? What is the minimum value of the deviation? That is called capital D. So, the derivation proves mu is equal to sin I by sin R. From the derivation, we can prove I is equal to A plus D by 2. R is equal to A by 2. I is called angle of incidence, R is called angle of refraction. We can prove I is equal to A plus D by 2, where D is called angle of minimum deviation, A is called angle of the prism. Then the refraction through a prism final formula will be mu is equal to sin A plus D by 2 by sin A by 2. Sin A plus D by 2 divided by sin A by 2. Just introduction alone, we have seen. No derivation, introduction alone. Refraction through a prism. Okay, next step. Convex lens and concave lens. Convex lens. Two spherical surfaces. This is one spherical surface. This is another spherical surface. This is convex. Two spherical surfaces not in contact, but slightly away. Combined, this is called concave lens. Sir, concave mirror we have seen, real image. Like that, convex lens also forms a real image. Suppose you have a source of light, object. Light is incident. After refraction, it is brought into focus. Distance between object and the lens, we call it as U. Distance between lens and image, we call it as image distance D. So real image you are getting in convex lens. Whereas in the case of concave lens, after refraction, light bends away. It is not brought into focus. Concave mirror, convex lens forms a real image. Convex mirror and concave lens forms a virtual image. Only basic information. Sir, while manufacturing the lens, what formula they are using? We know the refractive index of that particular material. We know the focal length of the given convex lens. Then, how they are manufacturing, what formula they are using? That is called lens maker's formula. Lens manufacturer's formula. Meaning, sir, in the case of a lens, we have two spherical surfaces. Two spherical surfaces means you complete this point. This is called radius of curvature R1. You complete this side. The radius of curvature for this one, R2. So your formula should include both R1 and R2. The formula says 1 by F is equal to mu minus 1 into 1 by R1 minus 1 by R2. You know very well F is the focal length of the given lens. Mu is called the refractive index of that particular glass. R1, radius of curvature of one spherical surface. R2, radius of curvature of the second spherical surface. So this is called lens maker's formula. No, sir, lens formula only I want. No problem. Lens formula. 1 by V minus 1 by U is equal to 1 by F. This is called lens formula. Lens maker's formula and lens formula. Okay. Good. Next. Suppose two or more lenses we are using together. Combination of lenses. Combination of lenses. First lens, second lens. Principal axis, this is the object. L1, L2. Light is incident. After refraction from the first lens, light forms a final image, I dash, at this point. Now, this I dash serves as a virtual object for the second lens. Virtual object for the second lens. Then final image. I. So object distance U, first image distance V dash, second image distance V. We can find the relation 1 by F1 is equal to 1 by V minus 1 by U, first lens. 1 by V dash minus 1 by U. Second lens, 1 by F2 is equal to 1 by image distance minus 1 by object distance. For second lens, this I dash serves as a virtual object. That is, light has come to this side, man. Again, it cannot go back that side. So this I dash serves as a virtual object for the second lens. Object you need, but that is virtual. So the object distance here is V dash. So I can write V dash. Therefore, 1 by F is equal to 1 by F1 plus 1 by F2. 1 by F1 plus 1 by F2 we add 1 by V dash minus 1 by V dash cancelled. What will you get? 1 by V minus 1 by V. Same. Single lens, what formula you have? Same formula you have for two different lenses. Use 3 lenses, 4 lenses, n lenses you use. Final formula will be 1 by V minus 1 by U only. This is called combination of lenses. 2 lenses or more. The resultant will be 1 by V minus 1 by U. Clear? Dispersion of light. You take a prism. This is the screen. You are allowing white lights. White light is incident. When white light enters the prism, it splits into 7 colors. That is called dispersion of light. Splitting up of white light into its constituent colors. So, it splits from violet up to red. Violet is the most deviated ray. Red is the least deviated ray. So, from the actual path, this we can call it as delta V. This we can call it as delta R. The dispersive power represented by omega. The formula is delta V minus delta R by delta. Ratio of this delta V minus delta R, we call it as angular dispersion. Sir, only violet and red we have to use, sir. Not necessary. Any 2 colors. The difference between the deviation, we call it as angular dispersion. Divided by unit deviation. Unit deviation means divided by normal deviation of the mean color. Violet and red means mean delta value. Green and blues are blue, green, average value of delta you write. That's all. Mu V minus mu R by mu minus U. Only the final formula we are writing, ma. Mu V, refractive index for the violet ray. mu r, refractive index for the red ray. Sir, that time you told refractive index is a constant. Then how come you are getting mu v and mu r here? Refractive index formula is what? Sin I by sin r. Angle of incidence is fixed, whereas angle of refraction differs for different colors. Every color angle of refraction is not a constant. It varies. So because of that, refractive index also changes. Clear, Amma? So this ratio, delta V minus delta R by delta, or mu V minus mu R by mu minus 1. This ratio is called dispersive power. Here. So these are the basic information regarding the light chapter. Some basic definitions also we can give for interference of light, diffraction of light, polarization of light. It's a huge topic, man. Only the definition part I am giving here. Interference of light, diffraction of light, polarization of light. Nature of light. One particular scientist argued that light is in the form of corpuscles. Newton's corpuscular theory. Light behaves as waves only. Heisenberg's wave theory. No, electromagnetic waves only it is moving. Maxwell's electromagnetic theory. Light is behaving like a quanta. E is equal to h nu energy. Quanta or wave packets. Planck quantum theory. 4 different theories means what we will use, sir? Wave theory only throughout we are going to use. Because wave theory proves all the basic concepts of light. Reflection, refraction, interference, diffraction, polarization. These 5 topics clearly proved by Huygens wave theory. So in that reflection and refraction, already we know wave theory also can prove laws of reflection and refraction. Wave theory can explain interference of light, diffraction of light, polarization of light. So only the definition part we will see. Interference. Superposition principle. 2 or more waves when they combine, the displacement will be added together. Y is a total displacement, means that is the vector sum of individual displacements, y1 plus y2 plus y3 etc. Here we are going to take only 2 sources. Source A or source S, light source. Single source here we are taking. Why? Later. It passes through 2 slits. Light passes through 2 slits. Slit means narrow rectangular opening. So light rays coming out from S1, light rays coming out from S2. These 2 combine, alternate bright dark fringes you are getting. That is called interference of light. These 2 sources, S1 and S2, it is not separate source, man. Only one source here we are having. S1, S2, we call it as narrow opening. It allows the light to pass through. That's all. It is not emitting any light. This is called interference of light. Next, diffraction of light. Only the definition we are seeing. Here we have an object. Here we have a screen. Allow the light to pass through. Allow the light to pass through. Here and all you are getting light, no problem. Here and all you are getting light. But here light rays are bending. Bending of light rays around the edges of an obstacle. Here it is not fully dark. This is a screen. This is an obstacle. You are allowing light to pass through. After coming out of this obstacle, some rays of light bend around the edges of an obstacle. That bending of light, you can see some patches of light above and below. Correct, Amma? So this is called diffraction of light. Polarization of light. Light waves are transverse in nature. In nature, we know whether it is transverse or longitudinal. Light waves are transverse in nature, we are going to prove. Polarization proves that light rays are transverse in nature. Light behaves like a wave. Whether it is a transverse or longitudinal wave, we are using polarization. This phenomenon proves light waves are transverse in nature. So these are the three basic information, only the definition of interference of light, diffraction of light, polarization of light we have discussed. Thank you. We'll continue.